Hi, everyone. Mr. Soboleski here. I'm working on a three-part video series covering pretty much everything you need to know from Unit 1 in our World and Chemistry curriculum. So it's going to be part 1. We're going to talk metric units and prefixes, measurements or scale readings, sig figs, and sig fig operations. I plan on keeping a little topics list running in the top left. So if you want to just skip through the video to whatever part you want to get to, if you look in the top left of the screen, you should see the topics there. So jumping right in. Starting with metric units and prefixes. So there are really two measurement systems that we use here in the US, the SI system or metric system and the USCS system, United States Customary System. These United States Customary System units are your classic American units, your gallons, cups, pints, your inches, feet, miles, your pounds. We're not going to be using these in science. Instead, we're going to be using the metric system or SI. SI comes from the French System International. These are all of these units you've been using in science, hopefully your whole life. It consists of a base unit and a prefix, if applicable, or just a base unit. Let's talk about what these base units are. So the base unit for length in the metric system is the meter, meter unit cube. For example, if I had a big box and I said, find me the volume of this box, you probably wouldn't get a mega graduated cylinder to see the displacement. No, so the length, the width, and the height, and meters, you're going to get meters cubed. Or more realistically, centimeters, 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 you're going to get centimeters cubed. So I can even write or meters cubed. For mass, we measure mass in grams. So you would probably think grams are the official base unit, but actually for mass, the base unit is the kilogram, which is lowercase k, lowercase g. But grams are commonly used. This is the one unit that includes the prefix there. So centi, milli, kilo, and then there's a lot of less common ones as well. There are other base units. These are just the three most common when it comes to measurement. For example, the base unit of, or the SI units for will be either degrees Celsius or Kelvin. You will learn the difference in it too. Fahrenheit would be the USCS unit. For the amount of a substance, meaning like the number of particles, we're going to count those in moles. If you go into physics, you'll talk more about voltage. So there are other base units in the metric system. These are kind of the three that have to do with measurement. Let's talk about these metric prefixes. Kilo was one that I mentioned already, and I'm sure you know several others. So I'm going to compile it onto the page. It's up to your individual chemistry teacher to talk about what you need to actually memorize. I do have what I call the rapid fire conversions that I expect you to be able to quickly. Okay. The common. We should always consider the base unit right in the middle. I think I'm going to try to write these at like an angle so I can fit more of them in here. Base unit. All right. So what is your base unit? Your base unit is like your meter, your liter, or your gram. It's the unit without any prefixes. Let's start with the larger ones. So above the base unit, we have deca, D-E-K-A, abbreviated DA. I have seen that spelled D-E-C-A before as well. Above deca, we have kilo, which is lowercase k. And what's the difference in size here? The difference in size is 10 times. 10 times 10, 10, And what's 10 times 10 times unit to kilo is 1,000 times bigger. In other words, there are 1,000 kilograms. Oh, I said that wrong. 1,000 gram kilogram, 1,000 liters in a kiloliter, which is not a common one, 1,000 meters in a kilometer. Above kilo, we have mega, capital M. We have giga, capital G. We have tera, capital T. And so on. There are plenty of other ones. If you're savvy, you probably know about kilobytes, terabytes. Let me see if I can undo what I just did. And 1,000 times bigger there. There we go. Okay. So again, these are several of the prefixes, some of them a lot less common than others. Let's look at the small prefixes. So what's smaller than the base? Abbreviated lowercase d. Then we have centi. Lowercase c. And milli, 1,000 millimeters in a meter. Millennium. So keep that in mind. Cents and a dollar. How many centimeters a meter? Let's list some of the even smaller ones just for your reference, which is that up to a U. That's 1,000 times smaller. Below that, we have nano, lowercase n, and below that we have picos, just like above. It's 1,000 times smaller, 1,000 times smaller, and 1,000 smaller. So as I said, it's kind of up to your individual chemistry teacher what you should memorize. We do kind of meet and tend to agree on these. So it's not like anyone's going to make you memorize these and then have another teacher at the same level only memorize a couple of them. But we do have quite a lot here. You probably learned in middle school kilo down through milli with a little phrase. I believe the most common one I've heard is King Henry died by drinking chocolate milk. That because when you include the by in the middle, that's your base unit. I have heard other phrases where it skips the base unit. King Henry died drinking chocolate milk. I don't like that because then it shows you then other times to decimate. So I like that base unit step in there. The slide I have is what I call the prefixes. These are, regardless of your level of chemistry, 1, 2, 3, AP, these are the ones you should be able to say. For example, if I tell you you have 1 meter, you should be able to tell me how many centimeters you have. How many cents in a dollar? 100. How many centimeters in a meter? 100. Another rapid fire conversion to know would be kilometer. So what is a kilometer? Well, it's 1,000 meters. So 1 kilometer is 1,000 meters. What else do we know quickly? Millimeters. That's a common one as well. Millimeters are very small. So the smaller the unit, the bigger the number. The bigger the unit, the smaller the number. Okay, a meter is bigger than a centimeter. So we have a smaller number for the bigger meter, a bigger number for the smaller centimeter. Credit Mr. Lucy for that little way of thinking about it. It's a great little way of thinking. A kilometer is bigger than a meter. So the bigger unit gets a smaller number. The small unit gets the bigger number. So, okay, so small number for the big unit, big number for the small unit. And one last one, kind of a derivative of these. If a meter is 100 centimeters and a meter is 1,000 millimeters, what's the conversion between a centimeter? A centimeter must be 10 times bigger. That's good to know. Go with 1 centimeter equals 10 millimeters. The base unit I chose for this slide here is meters, but this works with liters. 1 liter is 100 centiliters, not very common. 1 kiloliter is 1,000 liters, not very common. 1 liter is 1,000 milliliters. There we go. We use milliliters all the time. Grams, it works with grams too. Grams, milligrams, grams, this all works with those as well. So these are what I call the rapid fire. You should memorize these. And when I say no, I should say memorize. And memorize in that you're able to kind of come up with them within a couple seconds, not really think about it for 30 seconds. You should know this quickly. Okay, so that wraps up the metric system and the metric prefixes. Let's move into measurement and scale reading. Okay. You've been reading your whole life. We trust you. We just want you to think a little deeper about how to report your measurements when you make them. The phrase I started saying this, you are 1 better than your measurement device. Now, obviously, I'm not judging the measuring device you're holding in your hand when you're taking measurements. Obviously, we are more than that. But when it comes to measurement, your measurements are 1 better than your measurement device. Here's what I mean. Look at this picture of this ruler here. So let's assume that the 1 and the 2 are centimeters. So this would be like a meter stick with 100 centimeters. So that big 1 is 1 centimeter and that's 2 centimeters. What place does this measurement device measure to? Well, we have lines from 1 and 2, and we have 10 lines between them, meaning each of these lines is the 10th place. You're 1 better than that, 1 more detailed than that. So if this measurement device measures, you're going to measure to the 100th place. That's probably what you would have said even if I didn't give you this whole spiel. If I showed you this and said, what is that? I'll bet you said, well, let's see, that's 1, 1.2. It looks like about 1.1. See how that's 0.15 measurement you would make any true. You are 1 better than your measurement device. If this measurement device has lines for every 1 and lines for every 10th, you are 1 better than that. You gave me the 100th place. And this measurement here really consists of knowns and unknowns. Known digits are the 1 and the 1. What do I mean by known? Well, looking at where the triangle falls, I know that that triangle falls between the 1 and the 2. There's no disputing that, no debating that. I also know that it falls between the 1.1 and the 1.2 line. There's no disputing that. That is known. What is unknown and what is estimated is the 5. I judge it to be exactly slightly different. That's fine. And that's no more correct or incorrect than my guess. If you call that 1.14, totally fine. If you called it 1.16, totally fine. But what you can't do is go below that in terms of the quality of the measurement. For example, you can't say, I kept thinking it was 1.5, or maybe it was 1.14. So you know what I did? I split the difference. And if you split automatically, plug it into your calculator, what do you get? 1.15. That is halfway between these two numbers. But then, that is too detailed for this measurement device. In this case, you are 2 better than your measurement device, which is no. Okay, hold on. Yes, but we can only get to a certain level of detail with our measurement device. In order to get this level of detail, you need to have a meter stick that has lines for every hundredth place, so you can give me the thousandth place. You are limited by your measurement device. If your measurement device, like here in the picture, shows you the 10th place, you give me the 100th. Okay, a lot of talk. Let's another meter stick, actually. Now, before you think about it too hard, what would you call that? Just off the fly? Probably like 1.2, right? Maybe 1.3. And again, centimeter. That's our unit here. Yeah, and this would be a correct. This measurement device has lines for 1 and 2, meaning the ones place. You are one better than that. You're going to measure to the 10th place, which is what we did right here. Now, what if you called that 1.3? Is that wrong? No, that is just as correct as 1.2. Your estimate is that last digit, and as long as it's reasonable, your answer is correct. You know, if you call that 1.5, okay, now that's definitely not correct. But 1.2 is fine. 1.3 is okay. Even 1 would be okay. That last digit's up to you. Pause the video, try these out, and then unpause it. Let's go through them. Okay, let's look at what we have here on the top ruler. So you are one better than your measurement device. This top measurement device, you are going to be one better than that. What does that mean? That means you're going to go to the ones place. To the ones place. So 210, 220, 230. That's going to be about 235 or so. And if we assume it's centimeter, this one, 300, 310, 320. So that's going to be, I don't know, maybe 317. Notice I went to the ones place. I went one better than my measurement device. Down here, we have 7, 8, 9. So that's the ones place. I have 10 lines in between, so that's the 10th place. Now I'm going to go to the hundredths place, just like on the first slide we showed. So this one is between 7.0 and 7.1, maybe a little more than half. I think I'll call that 7.06 centimeters to the hundredths place. Over here, let's see, that's 8.5. So it looks like about halfway across. I'll call that 8.55 centimeters. Okay. Now, what if it falls on the line? Here's where it's a little trickier. Here's where it's trickier. But if you think about it as you are one better than your measurement device, it's actually not tricky at all. It's the same rule. Look at the ruler up top. What do we have? Well, we have lines for every 10, and we have 10 lines in between those. So we have lines for every 1. You are one better than your measurement device. That means you're going to give me the 10th place. So every measurement you take is going to be measured to the 10th place, also known as 1 decimal place. So if you judge this one to be right on the 23 line, you're going to call it 23.0 because you're measuring it to the 10th place. If you judge that to be right on the 30, you're going to call it 30.0 because you're measuring it to the 10th place. Remember, there's nothing weird you have to think about. Some people get in this habit of, if it's on the line, just add one more zero than you normally would. That's not correct. I mean, it'll get you sometimes, but not all the time. Notice there are 2 zeros here and 1 0 here. Okay, the rule is add 1 extra digit beyond what's in the meter stick, the ruler. All right, looking down at the second one, we have 1, 2, and 3, meaning each of these lines is the 10th place. You are one better than that. You're going to go to the hundredths place. So if you judge this to be on the 1.4 line, you're going to go with 1.40 because that's the hundredths place. If you judge this to be on the 3 line, you're going to go 3.00 because that's the hundredths place. By the way, something I should have said, what if you don't judge it to be exactly on the line? I mean, I tried my best to put the pixels right on the line, but if you judge it to be just to the right or to the left, is that wrong? No, of course not. Your guess is your guess. For example, for this first one, if you judge it to be just to the right of that and call it 23.1, that's fine. That's a correct answer. All that's really important is that you seem to be close to where it's pointing and that you have the correct number of decimal places. So that's correct. All right, looking at the bottom here. 600, 700, 800. Okay, so we have lines for every 100 and we have lines for every 10. You are one better than that. You're going to go to the ones place. Oh, but this one's a little tricky, isn't it? This one falls on the 640 line. What's the problem? That's not correct. Why is 640 not correct? Because the number 640 is not rounded to the ones place. 640 is rounded to the tens place. And even if you're saying, no, I mean for this to be to the ones place, trust me, like I believe it's on the one. Just writing 640 alone is not going to do that. We're going to use a special little chemistry tip here, you can use it for all science. If you put a dot after that and call it 640 point centimeters, I know it looks weird, but that's a good way of expressing that this is actually 640 rounded to the nearest ones place. It is not this 640 centimeters, because 640 is rounded to the nearest tens place. So 640 point centimeters. If you judge this to be right on the 700 line, you're going to call it 700 point centimeters. Although that one, now that I look at it, kind of looks like it's a little bit to the left. I might call that 699. And that would be an acceptable answer as well. Okay. One more slide of practice. I think one of them might be blocked by my little Zoom window down there. So just however many you can see, pause the video, write these down, and then unpause it and we'll go through them. Okay, so for the top meter stick, let's see, we have lines for every one, because we have 9, 10, 11. So that's the ones place. And we have 10 lines in between. That means the tenths place. You are one better than that. So you're going to go to the hundredths place. So every measurement we take should be to the hundredths place, 2 decimal places. All right, so for this top one, that's 9.5. I'd say about 9.53 in centimeters if this is a centimeter ruler. This one I'm judging to be right smack dab on the 10. So I'm going to call this 10.00 to the hundredths place. The next one, that looks like it's right on the line there. Which line is that? That's the 10.6 line. So I'm going to go to the hundredths place and call this 10.60. Okay. Now, what should be the same about every single number you make on the same meter stick? What should be the same? Not the number of digits or the number of numbers. It should be the number of decimal places. Notice 9.53, 2 decimal places, 10.00, 2 decimal places, 10.60, 2 decimal places. If this theoretically went beyond 100 and you called it like 102.75, 2 decimal places. Or if you go to the left all the way past 1 and called it like 0.82, 2 decimal places. Every number on the same measurement device will have the same number of decimal places. All right, looking at the second one. So I see lines for 10, 20, 30, and I actually don't see any lines dividing them. So that means we are limited to one better than this, the ones place. So that's 10, that's 20. Yeah, it looks like I'm kind of torn between 15 and 16. I can't split the difference and call it 15.5. You cannot do that. So I'm going to call this 16. This one, I seem to be right on the 20. What am I going to call it? Well, I have to go to the ones place. How do I do that? 20 point, not 20.0 and not just 20. All right, last meter stick here. I have lines for the 100. I have lines for the 10. You're going to be one better and give me to the ones place, just like we did above. So this one seems to be on the 240 line. If I'm on the 240 line and I'm going to the ones place, I'm going to call that 240 point. This one here, 310, 320, it's about 326, I'd say. So that goes to the ones place. All right, I think that's it for measurement scale reading. Yep. Next, sig figs. Sig figs is often a daunting topic for students. It is an important one though. What's important about sig figs is that we need to be able to match the quality of our calculations to the quality of our measurements. If I measure a length and a width very carefully with a very high quality meter stick with lots of digits, like lines, dividing lines, I'm going to get a good quality measurement that gives me a good quality calculation. If I use a poor quality measurement, I'm going to get a poor quality final answer, and that needs to be reflected in the sig figs. Sig figs are all about confidence in our data. It's very important to know. Here are the rules for identifying how many sig figs are in numbers. You've probably seen some version of this before. So I'll just run through these quickly. I'll list some examples as we go. Rule 1, all non-zeros are sig figs. That's the easy one. So if I have 13 meters, 2 sig figs. 12.75 grams, 4 sig figs. Let me write the numbers of sig figs. So that's 2, that's 4. Sandwiched zeros are sig figs. What are sandwiched zeros? It's zeros that are between non-zeros. So for example, if your measurement comes out to 206 grams, 206, that zero counts 3 sig figs. Or if we have 1.709 millimeters, that zero counts 4 sig figs. Leading zeros are not sig figs. What are leading zeros? It's any zeros before the first non-zero. For example, 0.0032. Those zeros do not count. Can you ignore them? No. Are they necessary? Yes. Are they important? Yes. They're necessary. They're important. They're hugely essential, but they're not considered sig figs. They don't contribute to the quality of the measurement, the detail of the measurement. All they do is they're like placeholders. They tell us how large an order of magnitude that is. Is this 32 tenths? Is it 32 hundredths? Is it 32 thousandths? No, it's 32 ten thousandths would be this measurement. It just tells us like the place. It doesn't contribute to the detail. So 2 sig figs in this number here. Another example of leading zeros would be, 0.79. That zero is, of course, optional, the front zero there. So that's not going to count. That'll be 2. Or one more example, 0.0003. How many sig figs? 1. Only the 3 counts. Trailing zeros. Trailing zeros are definitely the trickier ones. Notice there's 2 rules. Trailing zeros in a number with a decimal are sig figs. Trailing zeros in a number without a decimal are not sig figs. Let me address the purpose of those zeros to kind of make sense with this. A number with a decimal with zeros at the end. 32.700 grams. What role do those zeros really have? I mean, in math, they're not really necessary because 32.7 grams is the same as 32.700 grams in a mathematical or a theoretical sense. But in science, there is a difference. And now we know the difference because we talked about measurement. This measurement up top was measured with a much higher level of confidence than the one below, a much better quality balance. So it matters. These zeros up here, these zeros exist to improve our level of confidence, to increase our confidence in the numbers. These count as sig figs, 5 sig figs here, compared to, of course, 3 sig figs here. So when the trailing zeros exist to increase the detail of the number, they count as sig figs. Or in other words, if there's a decimal point anywhere in the number, the zeros are significant. So if we have 2.00, 3 sig figs. If we have 490 point, that's that weird trick we talked about, 3 sig figs. Okay. Anytime you have zeros at the end, if there's a decimal, they count. Let's now address trailing zeros in a number without a decimal. How many students go to Wilton High School? 1,200, 1,300, something like that. So if I told you 1,300 students go to this high school, Do you really think it's exactly 1,300? I mean, it might be, but if I say 1,300, you're probably thinking it's something close to that. So when I say 1,300 students, what do these zeros really do? They do the opposite of what these zeros did. They round off the number. They actually take away from the detail of it. They're used to round off large numbers. These are not significant zeros. Are they optional? Of course not. Because you can't say there are 13 students at the high school. No, you need to include the zeros. They just don't add to the detail of the measurement, and therefore they are not significant figures. 2 sig figs in this number. Now, what if you say, oh, Mr. Sobolewski, I actually counted, I looked at the roster. No. There are exactly 1,300 students. How would you reflect that? Well, if you know it's 1,300 to the nearest one, put a point there, and boom, there's your 4 sig figs. All right, just another example here. If I take a measurement and it's 690 grams, that would be 2 sig figs, or maybe even a larger number. If we have like 1 million meters, if I measure something as 1 million meters, how many sig figs? Just 1. Okay, so those are your sig fig rules. Why don't you pause the video, try identifying the number of sig figs, and then play the video, and I'll go through these. Okay, I'm going to do these pretty rapid fire here. 5,080, 3 sig figs. The front zero counts, or let's just say the 508 count, because that's a sandwich zero. The back zero does not count because it does not add to the precision. It rounds it off. Or in other words, no decimal place, not a trailing zero that's significant, not a significant zero. 41.21, easy, 4 sig figs. They're all non-zeros. 62,100. I see zeros at the end. Do I see a decimal place? No, not sig figs. 3 sig figs. 0.003, leading zeros, never count, 1 sig fig. 7.00, I see zeros at the end. Do I see a decimal place or a decimal? Yes, I do. They count, 3 sig figs. And it makes sense because the purpose of those zeros is to add to the confidence of that measurement. This number here, 0.000550. All right, I see zeros in the front and the back. The front zeros do not count ever. The back zero counts if there's a decimal anywhere in the number. Yes, there is. Therefore, this has 3 sig figs. 510 point. We've talked about that. 3 sig figs. It means they all count. 600.0. I see 3 trailing zeros. Not just that one. There are 3. Trailing zeros are anything after the last digit, the last non-zero. Do I see a decimal in the number? Yes, I do. Therefore, they all count, 4 sig figs. I sometimes get students that will call this 2 sig figs. They'll say, well, the 6 counts definitely, and the 0.0 counts, because anytime you have a decimal point, anything after the decimal counts. Well, yeah, but everything in between always counts. You can never have non-significant digits in the middle of a number. Never. They're only ever going to be at the front if they're leading zeros, or at the back if they're trailing zeros with no decimal place. 4 sig figs. 100,000, 1 sig fig. 92.3200. Trailing zeros with a decimal place, yes, they count, 6 sig figs. 0.870. I see a leading zero and a trailing zero. Leading zero never counts. Trailing zero, is there a decimal? Yes, it counts. 707. I see a sandwich zero. That's a sig fig. 140. I see a trailing zero. There's no decimal. 2 sig figs. That one does not count. I think there's one being blocked by my little Zoom window. A new set. Go ahead. Pause the video. Try these out. Okay. Up here, I have leading zeros, which do not count. 2 sig figs. 400.2. I see sandwich zeros. Of course, they're going to count. 4 sig figs. 67.9. Easy. 3 sig figs. 0.01 or just 0.01. That's a leading zero, does not count. I only have one sig fig right there. 42.790, trailing zero, after a decimal, yes, it counts, 5 sig figs. 3,000, 1 sig fig. 0.0087100. Leading zeros do not count. Trailing zeros only count if there's a decimal, which there is. 1, 2, 3, 4, 5 sig figs. The 87100 are significant. 12.70, 4 sig figs. 82.800, 5 sig figs. Those trailing zeros count because there's a decimal. 52,000, 2 sig figs. Scientific notation, 5.29 times 10 to the 8th. In scientific notation, you only look at the front number down here, like the large number down in front. That determines your sig figs. This number has 3 sig figs because 5.29 has 3 sig figs. The 10 to the 8th do not count as sig figs. In fact, even if you wrote this in numerical form, it would be 529,000,000 or 529 million. That would also have exactly 3 sig figs. There's one blocking here. I think it's like 3.00 times 10 to the -4th, if I remember. Again, you look just at the front number, and if that front number is 3.00, then this number has 3 sig figs. Okay. And that leads us to, one other important concept of sig figs is being able to round off sig figs, round off numbers to the appropriate number of sig figs. 870.2604. Let's practice rounding that off. Okay, if I need to round this off to 1 sig fig, I'm going to use trailing zeros to help me do so. This number is going to round to 900. Sometimes it's easier to just see the answer and then be like, oh, I see why that makes sense. So I only can use one non-zero here, and the rest are going to be zeros to round it off. I'm not going to call it 800 because the 7 rounds up. So this is going to be 800. What about 2 sig figs? Well, now I can put 2 non-zeros. So the 8 is definitely going to be an 8, and the 7, I pause and say, is that going to stay a 7 or is it going to go up to an 8? Well, there's a 0 next to it, so it's going to stay a 7. And this is going to be 870. 3 sig figs. 870 is what I see in the number there. But what's the problem with me writing 870? Notice that's only 2 sig figs. It matches what you said above. So how do we make this have 2 sig figs? What you cannot do is add an extra decimal place. That would be 4. So we're going to use our trick and say 870 point. By the way, you could also use scientific notation. 8.70 times 10 to the 2nd. Remember the last one, 4 sig figs here. 870 point. Okay, now we got to ask ourselves, are we rounding up or not? So 870.3 is what we're going to say here. 870.3 because the 6 makes a 2 round up. 5 sig figs. 870.2, and now I ask, is the 6 staying or raising up? It's staying. 870.26. Finally, 6 sig figs. The 4 at the end means the 0 stays. It's going to be 870.260. All right, maybe you could pause and try this one on your own. All right, 1 sig fig. Keep in mind, these zeros are not sig figs. So we're going to start this one off with 0.009. Okay, that's 1 sig fig. You can't just call it 9 or 0.9. Then you would be drastically changing the number. No, you use those leading zeros, which are not significant, to fill in the placeholders until you get to your non-zero, your sig fig. 2 sig figs. So we have 9206. So the 92 is going to stay as 92 because there's a 0 after it. 0.0092. 3 sig figs. The 6 will make the 0 go up. 0.00921. 4 sig figs. Well, my number originally had 4 sig figs. 0.0092 0.06. 5 sig figs, well, here's the problem. We don't have 5 digits. But if there is a decimal, you can make it more sig figs. In fact, any number you can by adding decimal places. We're going to stick a 0 at the end of this. If we are confident with this number up to 5 places, we're going to stick a 0 at the end as our 5th sig fig. 0.009260. Okay, 2 more to practice with. Go ahead and pause the video, try these, and then unpause it. Round this off to 1 sig fig is going to be 60. 2 sig figs, 63. 3 sig figs, 62.8. 4 sig figs, 62.80. This one down here with 1 sig fig, 0.04. 2 sig figs, 0.038, because the 5 makes it round up, 0.038. And finally, 3 sig figs, 0.0375. Okay. Hopefully we're good with sig figs and rounding numbers off to sig figs. Our last topic of this video, sig fig operations. When multiplying or dividing, which is what we're going to do 90+% of the time, you round your answer to the smallest number of sig figs. So you look at all the numbers that went into your calculation and you count the sig figs in those numbers. The smaller number of sig figs is what you need to round your final answer off to. So for example, let's say you're doing a simple area calculation. How do we find area? Length times width. 4.28 times 1.40. Calculator tells me 5.992. Let's talk about our unit first. Centimeter times centimeter, centimeter squared. Now for sig figs, we look at both of these numbers, we count the sig figs. 3 sig figs here, 3 sig figs here. We are limited to 3 sig figs in our final answer. So how do I round this number off to 3 sig figs? 5.99 centimeters squared. That's exactly what you report. Let's try another one. This one we can do in our heads. 4.00 times 5.00. 4 times 5 is 20. In fact, if you plug into your calculator 4.00 times 5.00, it's going to tell you exactly 20. But that's a problem. Because how many sig figs do we have here? 3. How many here? 3. We need 3 sig figs. How do we do that? 20.0. And my unit is centimeters squared. And hopefully this helps illustrate the importance of why we care about significant figures. If you multiply these sides together and say, oh yeah, the area is 20. Well, that's not a very good representation. I was very detailed in my length, 4.00. I was very detailed in my width, 5.00. And I'm now realizing that, yes, my 4 side is longer than my 5 side. Oops. We were very detailed. We measured with 3 sig figs. That's a lot of confidence. You can't just tell me 20. Come on. 20 could mean it's like 23. 20 could be, it's like 17. No. If I give you 3 sig figs in each of these measurements, you need to report 3 sig figs in your final answer because 20.0 shows an added level of confidence more than 20. In fact, it's, I would say, 2 levels of confidence because you go from 20 to 20 point to 20.0. That's the correct answer. Is that the same slide? Oh, no, it's not. 4.0, 5.0. So the calculator still tells us 20, but now we got to do something different. How many sig figs in 4.0? 2. How many sig figs in 5.0? 2. How do we write 20 with 2 sig figs? 20 point. That little trick we learned. 20 point centimeters squared. That's our answer. Or technically, you could say 2.0 times 10 to the first. Let's do a volume. 527 times 860 times 198. Calculator tells me 8,907,000. Oh no. 89 million. 737,560. My unit is millimeters cubed. All right. Looking at sig figs, how many sig figs in 527? 3. How many sig figs in 198? 3. How many sig figs in 860? 2. Now, what if your partner said, oh, no. I measured the 860. It was actually 860. Well, you would say, well, you would need to stick a point at the end if that was measured to the ones place. But if that's written as is, we have 2 sig figs. And actually, I'm realizing now, we're going to have a really interesting answer here, aren't we? You seen it yet? We're going to need to represent that red number in 2 sig figs. How do you do that? Well, you can't call it 89 million. Why? Because this number in red does not round to 89 million. The 7 rounds up. Well, can you call it 90 million? No, because 90 million is 1 sig fig. Well, can you stick a decimal point at the end? Can we do that? No, because now you just made it 8 sig figs. You can't do that. What can we do? There's only one thing left to do. Resort to our old friend scientific notation. It's the only way. In rare situations, I swear I didn't plan this. I just made up 3 numbers and it happened to work out this way. In rare situations like this, you need to use scientific notation in order to make this work. So I was planning on talking scientific notation in my next video. Looks like we'll have to do a little bit now. So I need to write 90 million in scientific notation, giving it 2 sig figs. 1, 2, 3, 4, 5, 6, 7. You always sweep it until the front number is between 1 and 9.9999 repeating. So I'm going to stop it between 9 and 0. This gives me 9.0. Those are my 2 sig figs. Times 10 to the, I lost count, 1, 2, 3, 4, 5, 6, 7. Times 10 to the 7th millimeters cubed. That's exactly how you need to report this one. It's tricky, it looks weird, but that's the only way to do it correctly. This works for division as well. This would be like a density calculation, mass over volume. 5.18 divided by 44.02. Calculator tells me 0.1176737846. How many sig figs in the top number? 3. How many sig figs in the bottom number? 4. I'm limited to 3 sig figs. I need to round this off. Looks like it's going to become 0.118, and my unit is grams per milliliter. Nothing cancels here with a gram and a milliliter, so you just list it just like that. I think this is one where I meant for it to be a weird one, so hopefully now we can get this one. 600, oh no, I think that's different. 605 centimeters cubed divided by 4.02 centimeters. Yeah, this one's a norm. Well, it's a little tricky, you'll see. So the calculator tells us 150.4975124. 4975124. How many sig figs in that top number? 4. How many sig figs in the bottom number? 3. How are we going to report this? With 3 sig figs. So you can't call it 150. You can't round it to 151. You have to call it 150 point. Now for our unit, centimeters cubed divided by centimeters. This would be like if you're trying to find an area, like the surface area of like a box. The cubic volume divided by one of the lengths or the heights will give you centimeters squared. It's like in math class, x cubed divided by x, x squared. All right, I think this is the one I was talking about. 373.3 millimeters times 3.75. 4 sig figs here, 3 sig figs here. My calculator tells me 1,399.875. I need to report this with 3 sig figs. Ah, there's a problem. See how this number is very close to 1,400? Well, I can't call it 1,400. That's 2 sig figs. I can't call it 1390 because this doesn't round to 1390. I'm going to need to use our old friend scientific notation. 1.40 times 10 to the third. And my unit is millimeters squared. Okay. Last thing we're going to cover here is sig fig operations when it comes to adding or subtracting. However, notice in red, ignore sig figs. We don't think about sig figs when we add or subtract. We look at decimal places instead, or really technically just places, meaning like the tens place or the hundredths place or the ones place. We look at the places. Round your answer to the smallest number of decimal places or places in the numbers you used. I thought I had another example here. I definitely did. Did I go out of order? Well, let's go through this one. So looking at these three numbers here, I have, again, I don't look at sig figs here. I go to the hundredths place, tenths place, hundredths place. The least quality measurement limits me. Which of these three is the least quality measurement? It's that middle one. It's the tenths place, or it's the smallest number of decimal places with one decimal place. So my calculator is going to tell me 20.39. So my calculator is going to tell me 109.47. I am limited to the tenths place. How do we round this to the tenths place? 109.5. And my unit is just centimeters. Now you might say, hold on, did you just create an extra sig fig? Because I had 4 sig figs, 3 sig figs, 4 sig figs. Well, yes, I did. But remember, we don't think about sig figs when we add or subtract. This is the correct measurement. I limited myself to the tenths place, which is the lowest quality measurement. This is exactly how you need to do this. Over here, 102 minus 15.82. Calculator tells me 86.18. My unit is milliliters. But I am limited not to sig figs, I'm limited to places. The top number is rounded to what place? The ones place, also known as 0 decimal places. The bottom number, 2 decimal places or the hundredths place. Which one is the poorer quality measurement? The ones place. I have to round this number to the nearest ones place, 86 milliliters. See there, technically I lost a sig fig, but again, I don't think of this in terms of sig figs when we add or subtract. All right, for larger numbers, decimal places really just means places, really for all numbers, such as the tens place, hundreds place, etc. So look at these large numbers here. When I add these up, this one plus this one plus this one, I get 16,262 meters. Now let's see where I'm limited. This one goes to the ones place. This one goes to the hundreds place. This one goes to the ones place. Which one is my least quality measurement? The hundreds place. I have to round this number to the nearest 100. The answer is going to be 16,300 meters. Now, what if this was 3 people measuring and the middle guy says, oh, no. It was actually 2,800. I swear, I measured it. It was exactly 2,800. What would you say? Put your decimal point there. Because now if you put your decimal point there, now we have measurements to the ones place. And if that were the case, your answer would be the full number, 16,262. See how the measurements determine the quality of your answer. All right, I believe that's it for this. Hope this was helpful. And continue on to part 2 if you need to review those concepts.